Hi, hi everybody. Sorry I'm not here today, but we will still get through 4.6, I think, without too much difficulty here. So 4.6 is called the method of undetermined coefficients. And specifically using the Annihilator approach. So we're going to be combining what we learned in 4.5 as well as what we learned in 4.3. So combining the differential operators, also still using the solutions to the homogeneous linear equations with constant coefficients that we spent some time with in 4.3. Okay, so the basic idea here, or the basic method really, is first we're going to pretend that the solution, or the differential equation that's given to us, is equal to 0. And so we're going to find that solution, and that's called the complementary function. Which we'll call y sub c. Okay. Second, once you know what solves the homogeneous version of the equation that we'll see, then you're going to annihilate the right-hand side to find a particular solution and then once you have the complementary solution, and by the way this is y sub p, and once you have the particular solution, then you just combine them, and that is the general solution for a non-homogeneous linear differential equation. Okay, so that's what we're focusing on today. All right, so let's just look at an example. And before we do some examples here, I should mention that this method that we're learning right now only works as long as we can annihilate the functions that the equation is equal to. So if you think about what we learned at 4.5, basically as long as we got a polynomial, an exponential, or like a sine or a cosine or any combination of those, we can use this method. In 4.7, we'll learn a different method that will work all the time, regardless of what kinds of functions there are. But for now, let's look at this example. Let's say we have d squared y over dx squared plus 3 times dy dx plus 2y, and let's say that equals 4x squared. Okay, so first we're going to go ahead and solve and find the complementary solution. So we're just going to pretend like this was equal to 0. And if we look at our differential equation, the auxiliary equation would be m squared plus 3m plus 2. Okay, so we set that equal to 0, factor, so m plus 2 times m plus 1. And now we get our roots, which are negative 2 and negative 1. And from there, we can build the solution for the complementary function. And so using these two roots, we have c1 e to the minus 2x plus c2 e to the minus x. Okay? So again, first step, pretend that this is not even there and it's equal to 0, and solve it just like we have been. So find the auxiliary equation, find the roots, and there's the solution for that, which we call the complementary solution. The second step is now going to be to annihilate the function over here, 4x squared. And in order to do that, we have to use, so now think about what we learned in the annihilator section, or the differential operators section. In order to cancel out 4x squared and get it to go to 0, you'd have to use d cubed. In other words, if you differentiate this 3 times, that equals 0. And so now, what we're going to do, oops, this should say annihilate 4x squared by using, not use, d cubed. And so now what we're going to do is multiply the entire equation up here by d cubed. So now we're going to have d cubed. And by the way, I'm going to rewrite this now in differential operator form. So that would be d squared plus 3d plus 2 times y. And this should look just like the auxiliary equation, because it is. And now on the right-hand side, we'll have d cubed applied to 4x squared. And the whole point of this now is that on the right-hand side, this equals 0. And now on the left-hand side, we have a slightly new differential equation that we know how to solve. This translates to an auxiliary equation of m cubed times m squared plus 3m plus 2. And here we gain a new root, m equals 0, and it's a multiplicity of 3, so we have a repetition pattern going on there. And here, I mean, we still have the m plus 2, m plus 1 factors. And so I'm going to highlight this. This is my new roots. And then we still have the ones from before, -2 and -1. Okay, so now if I build the solution here, from here we'll get the general solution. Okay, so now we're going to have, since we have 0 with the multiplicity of 3, okay, that's going to be c1 plus c2x plus c3x squared. Remember that this is really e to the 0, but e to the 0 is 1. So we'll just have c1, c2x, and c3x squared. Plus, and then we still have from before the c4 e to the minus 2x plus c5 e to the minus x. Okay, and so now what you can see is that the tail end of this right here, this is the complementary solution, just with different constants, that we found in the first part. Okay, so that means then that the first 3 terms, which are brand new and we have yet to see, must be the particular solution. Okay, and so now, once we know what the particular solution looks like, we can kind of plug this into the differential equation to figure out what it needs to be. Okay, so what we're going to do is let the particular solution, and just to make things a little easier, instead of using the subscripts and all that, I'm just going to rewrite it as a plus bx plus c x squared. Okay, so we're going to start with that. And now we're going to, again, plug this in to the differential equation to see what needs to happen for a, b, and c in order for us to get 4x squared. So that means we got to find the second derivative, and we also have to find the first derivative. Okay, so first derivative for this function with respect to x will be b plus 2cx. And if I find the derivative again, the second derivative will just be 2c. And so now we'll plug that in. Okay, so we're going to substitute into the differential equation. All right, so now, again, here it is. Second derivative is just going to be this one, 2c, plus 3 times the first derivative, so that'll be b plus 2cx, plus 2 times y, and in this case the y is just a plus bx plus cx squared. Okay, and now that needs to equal the right-hand side, which is 4x squared. Okay, so now what we can do is, it's almost kind of similar to what we do with partial fractions. You want to compare the coefficients of all the terms that you have. So here, let me just rewrite this. This is 2c plus 3b plus 6cx plus 2a plus 2bx plus 2cx squared. Okay, and that must equal 4x squared. And so now what I mean by comparing coefficients is that over here we have constants with no x's. Okay, and so that would be, let's see, 2c, 3b, and 2a. So 2a plus 3b plus 2c, since we have no constants on the right-hand side, that has to give us 0. Okay? And now if we look at the terms that have x, so these guys right here, there's also no x term on the right-hand side. Okay, so these coefficients here, 6c plus 2b, also have to add up to 0. Okay, so what does that leave us with? So that leaves us with this 2c x squared, and that has to equal 4x squared. So in other words, 2c has to equal 4. Okay, and now you can solve the system. So if you see the 3 by 3 system here, this is not horribly difficult to find the solution. C is going to be 2. And now you can plug 2 into the second equation here. So we'll have 12 plus 2b equals 0. So then we're going to get b is equal to negative 6. And then we can plug those back into the first equation. So we'll have 2a minus 18 plus 4 equals 0. So 2a is going to be 14. So a is going to be 7. Okay? And so now what we just found is the particular solution. Remember, the particular solution looks like this, and we just figured out what these constants a, b, and c, in other words, these were the undetermined coefficients that I had, which are now determined because we figured them out. So the particular solution is 7, where's b? So minus 6x, and then plus cx squared, so plus 2x squared. And therefore, the general solution, remember the general solution is complementary plus particular using the superposition principle. So we're going to add the very first solution we got all the way back in step 1, which is this complementary solution right here, and then we're just going to add that with the particular. So the final answer is c1 e to the minus 2x plus c2 e to the minus x plus 7 minus 6x plus 2x squared. Okay? And so that's the first example. Okay? And so here's a recap of the method, and we'll do one more example. Okay, so first, you find the complementary solution. In other words, assume the equation equals 0 and find the solution like you normally would. Annihilate the function on the right-hand side. I guess if the equation is reversed, that's left-hand side, but at least the way we're setting them up. Annihilate the right-hand side. And now, from there, you'll find the general solution of the new equation. So after you annihilate and multiply both sides by a differential operator, you're going to go ahead and find the general solution here. And from that general solution, you use the non-duplicated terms to form the particular solution, y sub p. Okay. Once you know what the particular solution form looks like, you substitute that into the differential equation, and solve for the coefficients. Okay, and then the last step here, which I'm going to squeeze in on this page, is now the general solution. I lied. I'll put it over here. The general solution is now just whatever we had for the complementary plus whatever we got for the particular. Okay? So that's basically the method here. We'll do one more example together. And then the other skill that's really in this unit is not necessarily solving the entire non-homogeneous differential equation, but looking at it and knowing what the particular solution form looks like. So sometimes they'll ask you, what is the form for the particular solution, but not to solve the whole thing. And so we'll do that as well. Okay, so let's look at this example here. Say we have y double prime minus 3y prime equals 8e to the 3x plus 4 sine x. Okay, if it's all right with you guys, I'm just going to use d's exclusively now rather than writing the auxiliary equation in terms of m. Okay, so I'm going to follow my steps here. So first, I'll write this in differential form, differential operator form. And so from here, we know that d times d minus 3 needs to equal 0. This is the auxiliary equation. And my roots are 0 and 3. And so that means the complementary solution for this equation, if it were equal to 0, right, then that would be a constant. It'd be c1 e to the 0x, but e to the 0 is just 1. So c1 plus c2 e to the 3x. Okay? Second step. Now we have to figure out a way to annihilate this right-hand side. Okay? So for 8e to the 3x, we can use d minus 3 and now for the trig function, 4 sine x, there's no exponential attached to this, so this will just be d squared plus beta squared, which is 1 here. Okay. And so now from here, we build the general solution. Okay? So the general solution well, I guess I should write the equation out first. So I forgot that step, sorry. So if I look at the original equation in step 1, now we're also going to apply d minus 3 and d squared plus 1. And that is how we get 8e to the 3x plus 4 sine x to cancel out. Okay, because remember, we're applying to the whole equation these new operators, d minus 3 and d squared plus 1. And that gives us this on the left-hand side, and on the right-hand side we get 0. You don't have to verify that. At this point, you know that that's what's going to happen. All right. Once you have this written out, let me just write it out as d times d minus 3. Okay. And so from here, let's build the solution. So that was step 3. So the general solution will be, this has a root of 0, so c1 plus d minus 3, that's c2 e to the 3x, plus another root of 3 here, so that would give us c3x e to the 3x because we have a repeated root there, so we throw in the x. And now d squared plus 1, that translates to c4 cosine x plus c5 sine x. Okay, so now from here, we want to compare what we have. Whoop, I'm off the screen there. So from here, we want to compare this general solution to the complementary. So, and you can see my complementary solution, the way I've written it, matches my first two terms. Therefore, the particular solution is these last three. Okay? And so that's step 4. So now, and again, to make things easier, I'm going to use A's, B's, and C's. So my particular solution must look like ax e to the 3x plus b cosine x plus c sine x. And from here, now we're going to go ahead and substitute this into the differential equation. So we're going to have to find the derivatives. The first derivative will be, if I use the product rule, a e to the 3x plus 3ax e to the 3x plus, and then the derivative here, actually that'll become a minus b sine x, and then plus c cosine x. Then we find the derivative again. So that'll be 3a e to the 3x. Here we'll have to use the product rule again. So 3a e to the 3x plus 9ax e to the 3x. And now we differentiate signs. So that'll be minus b cosine x. And then this becomes minus c sine x. Okay, so now we're going to plug all those in. So that's step 5. Substitute. Okay, so looking at my equation, y double prime minus 3y prime is now going to become the particular double prime, so that's actually 6a e to the 3x plus 9ax, I combine these, sorry, 9ax e to the 3x minus b cosine x minus c sine x. Okay. Minus, I'm going to just go underneath here, 3 times y prime, so that'll be a e to the 3x plus 3ax e to the 3x minus b sine x plus c cosine x. And then all of that has to equal 8e to the 3x plus 4 sine x. Okay, so let's kind of group some things. It looks like we have several terms that have the e to the 3x. So let me rewrite that. We got 6a e to the 3x minus 3a e to the 3x the 9ax e to the 3x, you can see that those cancel. Positive 9ax e to the 3x, and then if you distribute this negative 3, that'll cancel out this term here. So the only exponentials we got is 6a e to the 3x and negative 3a e to the 3x. So that is going to be 3a e to the 3x. Okay? You know what? Let me write this down a little lower. 3a e to the 3x. Plus, and now what I'll do is group my cosine terms together. So if I look at the cosine terms, I have a negative b cosine, and I also have a positive negative 3c cosine. So that's what we have for the cosine term coefficients. Now we'll do the same with the sines. So we'll have negative c, positive 3b, so I'll do 3b minus c sine x. And again, that needs to equal 8e to the 3x plus 4 sine x. Okay? And so from here, you can see what needs to happen. We get that 3a, this is the only exponential on the left and on the right, so 3a has to equal 8. And let's see, as far as the cosine terms, on the left we have negative b minus 3c cosine, but on the right hand side we don't have any of them, so that negative b minus 3c has to be 0. And then 3b minus c, which is the coefficient of sine, that has to be equal to 4. Okay, and I'm trying to save some time here because I think I'm going to get cut off by the next class coming in. If you solve this system for a, b, and c, then you're going to get a equals 8/3, b is going to be 6/5, and c should end up being negative 2/5. If you want to pause the video and make sure that that's right, that's fine. So then, now what we have is the particular solution looking like this: 8/3 x e to the 3x plus 6/5 cosine x minus 2/5 sine x. And so finally, that was, where is the complementary? There it is. So our final solution is going to be c1 plus c2 e to the 3x plus this particular solution. Okay, so there it is. Okay, last example. Again, it's not solving the whole thing, but just finding the form of the particular solution. And here's a good one. Let's say we have y triple prime minus 4y double prime plus 4y prime. Let's say that equals 5x squared minus 6x plus 4x squared e to the 2x plus 3e to the 5x. Okay? So here's what we're going to do. Let's write this in differential form. So that'll be d cubed minus 4d squared plus 4d times y. And so from here we'll get d, that factors to d minus 2 squared then. Now I'm also at the same time going to look at this right hand side to annihilate. Let's see. For this polynomial, we're going to use d cubed. For this exponential, it needs to be d minus 2. And since we have an x squared in front, that's going to have to be to the third power. And then now we have just another exponential to the 5x, so that'll be d minus 5. Okay? And so from here now we can start building the general solution. So the complementary, using these roots from the first part, would be c1 plus c2 e to the 2x plus c3 x e to the 2x. And now we're going to use this to find the particular solution. So this is the complementary. Here's the particular. We have a root of 0, but keep in mind we've already used 0 twice here. Oh, sorry, right here. c2 e to the 2x. Let me backtrack, sorry. We've used the root of 0 once. Therefore, when we start 0 here, instead of just a constant, it'll be c2x. know what, let me use a different constant here, C4x, okay? Plus, we got to repeat that 3 times. So C5x squared, and then C6x cubed. All right, and now we also have, I'm going to squeeze this in here, d minus 2 cubed, but we've also already used 2 times. This is what I was getting ahead at. Sorry about that. So if we look at where we left off with C3x e to the 2x, we're going to pick up with x squared now for the next 3 times that we used 2. So we're going to have plus C7 x squared e to the 2x plus C8 x cubed e to the 2x plus C9 x to the 4 e to the 2x. And then finally, we have this 3e to the 5x, so that'll just be plus C10 e to the 5x. So the d minus 5 gives us the C10 e to the 5x. So all of this stuff over here is the particular solution. So my general answer is going to be, if I write it with just a's, b's, and c's, ax plus bx squared plus cx cubed plus dx squared e to the 2x plus ex cubed e to the 2x plus fx to the 4 e to the 2x, and finally plus g e to the 5x. Okay, so you don't have to solve the whole thing, but if they do ask you to find the particular solution, you kind of have to figure out what terms you need in order to build it. All right, so that's the end of 4.6. I'll see you guys on Tuesday.